Hey everybody, today I'm going to talk about Scoreboard Inference, which is the last meta career question, level 2. Unfortunately, this question has stumped me, and I've gotten close to solve it, but I haven't solved it. I haven't managed to solve all the test cases, so this is going to be an incomplete solution because I just don't I don't have the solution right now, and I don't want to look it up. Maybe eventually I'll get it. So let's go over some common approaches. So in the scoreboard inference is a problem that already appeared in the level 1 problems, but it has a little bit of an upgrade. So in the level 1, let me change to pen. Make sure I'm recording. Yes. So in the level 1 version of the problem, level 1, um, the problems can have either a point value of 1 or 2. But in this version, they can have a point value of 1, 2, or 3. And this makes 1, 2, or 3. And this complicates things a lot. So let me just go over the problem again because you might not have seen the level 1 problem. So you're given an array of student scores. Let's just say 4, 5, 6 is something that is an example that I just came up with right now. And so what does this mean? So the students are taking a test. So this is a test, and student I scores SI. So for example, student 1 scored a 4, student 2 scored a 5, student 3 scored a 6, or 0, 1, 2, 3 if we start at 0 index. So now the problem statement is find the minimum number of problems necessary to allow your students to get the given scores. So what I mean by this is, for example, if the test only had one problem, so here's our test. If the test only had one problem and it has a point value 1, let's say. So there's one problem on the test and it has one, you can only get 1 point on it. Or yeah, if you get it, so these are binary problems. So either you get it, you get 1 point, or you don't get it and you get 0 points. So this has a point value 1, and there's only one problem. So then what is the maximum? So then the students are trying to take this test. There's no way that obviously they're going to get a point value of 4 or 5 or 6 because there's only one problem, right? And the maximum score that you can get on this test is 1, and the minimum score you can get is 0. So let me show you an example of a test that does work. So this test doesn't work for this. So it's not possible to construct a test that only has one problem. So even if you change this point value to a 3, you still wouldn't be able to get a point value of 4, 5, or 6. So it's not possible to construct a test which has only one point. Yeah, did I say that right? Which has only one problem, and get those have all those 3 students get those scores. So let me show you a test that does work. So here we have a point value 3, and then 2, and then 1. So there's 3 problems there, and this is the best. There can be multiple bests. You can have 2 different tests with different points, or so there can be multiple ways to get the best. Like maybe one test has 2 problems than a 3 problem, and it doesn't matter because it's enough, something like that. So this is the best. So how does student 1 get a score of 4? Well, he gets the first problem right, and then he gets the third problem right, but he doesn't get the problem with 2. So that's student 1. And then how does student 2 get 5? Well, student 2 gets these 2 and then doesn't get this one. And then how does student 3 get 6? Well, they get 3, 2, and 1. They get all incorrect. So that's how they get 6 points. So for example, if I were to add an 8 onto here, then we would need another problem. Why? Because 3, 2, 1 isn't enough to reach 8. So we would need either a 2 or a 3. Either one would work. I mean, we could also add 2 1s, but that would be inefficient. We're trying to find the minimum number of problems necessary. If we added 2 1s, of course, we could now hit 8 if the person who got 8 solved all of them 3, 2, 1, 1, 1. But that's inefficient. It would be more efficient to add a 2 and then have the student solve 3, 2, 1, 2. And that's only 4 problems that we need. So hopefully that kind of makes sense. So we're given an array of student scores. We're trying to find the minimum number of problems. We have to like invent what problems there are and what their point values are. So we're given an array of problems, and we need to determine, invent which scores there are, or like find the minimum number of problems necessary to allow your students to score the values that are given. So I guess a couple more examples. So if we're given 1, then obviously we only need 1 problem. If we're given 1, 2, then we need 2 problems. Why? Well, this can either be 1, 1, or it can be 1, 2, right? Right, so either the second student gets both, or he gets maybe the second one, and that's just enough. So, for example, 1, 2, 3. So evidently there's a couple of solutions. So 1, 1, 1. If there's 3 problems, then the last student gets all 3 right. The second student gets 2 of them right. But this is inefficient. Why? Because 1, 2 is enough to cover. So the first student gets the first problem, the second student gets the second problem only, and the third student gets both problems. So how do we go about solving this? Let me show you. So a couple things that I've noticed, or like that we can notice in this discussion right away. So this example I just gave with a 1, 1 and the 1, 2. So let's just say finding 1. 2 1s is never worth it. Never. And I mean never. Never worth it. It's always more efficient. Always more efficient to use 1 and 2. So why? Like basically, if you ever end up with 2 1s, you can always just replace them with a 1 and a 2. Why? Because if you need 2 1s, right, then that means that, I mean, I guess you're here. I don't know if I'm gonna have to eventually draw something like this. I don't know if it's gonna make sense, but so in this example, 1, 2, so student, I don't know how I think about this. Well, first of all, okay, I don't know, getting a little confused, but it's 2 is never worth it. Sorry, 2 1s is never worth it. Why? Because you can always replace. So let me give you an example. The example I just gave there, 1, 2, 3, right? So you can replace 2 of those 1s by, you can replace 2 of those 1s by a 2. And what happens then? So, well, since you can replace, I don't know, I'm getting it. The algorithm is definitely the confusing part here, but like this is obvious, right? You never want to use a 1 and a 1 because with a 2 you can hit the same distance as the 1 plus 1, and you can hit, because it's a 2, you can actually go 1 further. So if you were given 1, 2, 3, then with a 1 and a 1, this can't reach the 3, right? But with a 1 and a 2, this can reach the 3. You can go 1 farther. So you don't need to add you don't need to add more. Don't need more for the 3. More for the 3. Okay, finding 2. How do I go about this? So I guess if you have a lot of 2s, well, clearly, for example, if you have a lot of 2s, I don't know how many, a lot of 2s, can be replaced by 3s. So what do I mean by this? So let's just say we have the example 6, 8. So these are our student scores. We have 2 students. One of them scored a 6, one of them scored an 8. So we can obviously do this 2, 2, 2, 2. So there are 4 problems here, and that's enough to cover both, right? Because the first student gets 3 of them correct and then misses 1, and the second student gets all 4 of them correct. However, we can replace 3 of these 2's easily with a 3, 3, right? And that was only 2 problems. So this is more optimal than this. This is not the solution. Okay, so sometimes we can replace 2's with 3's. So when can we replace? We replace 2's with 3's. You know, if I knew the answer to this question, then I probably would have gotten all the tests correctly. But I have some intuition. So I think the way I see it is there's the special cases is well, actually, yeah, I'm not sure. So I tried multiple different ways to solve this problem, and the best solution I got 34 out of 35 test cases. So it's very close, but I missed one for some reason. I don't know. So when can we replace 2's with 3's? I don't know. I just like the problem is I don't know the answer. Yeah. So I can give you a couple different approaches to how I've approached this problem, but you know they might not be correct. So let's see. Let's try algorithm 1. I think this is my best one. So what I do is I keep track of a range variable. So range is how far we can currently go. Okay, look, here's also the issue. If you try to take greedy, like if you yeah, I guess let me write something here. So suppose I'm given something like this, 1, 7. Okay. The problem is that this 1, it has to, we need a 1. We need a 1. We cannot, we need a 1. 100%. Because somebody has a score of 1, we need a 1. What happens if we have a 2? Well, we need a 2. Like, we need a 2. What happens if we have a score of 3? We need a 3. And like very strong need. Because if we don't have these, if we don't have a 1 here, then, you know, it's going to be a bad time. However, if we have a 4, 7, for example, we can replace, we don't necessarily need a 1, is what I'm trying to say. We could use instead 2, 2, 3. So as you can see here, what happened is, I mean, I could have written this out 3, 3, 1. That also would have been fine for this example. But in my mind, I think there are cases when you can replace a 1 with 2 2's. So let's say, for example, you already have a 2. Like you already need a 2. You already have a 2. I guess a good example for this is 2, 4, 7. It's very similar to the one I just showed, but you need a 2 here. So 2, right? And then, well, the 4, right? Yeah, like, I mean, you need to reach this 4. So first of all, another thing I forgot to mention. The problems aren't ordered. Problems aren't ordered. So we should probably sort them. Probably should sort them. So given that we've sorted them, our algorithm is going to iterate over them in order from smallest to biggest, and I expect the algorithm to be O of n, right? So we do a constant amount of work for every single question that we look at from biggest to smallest, from smallest to biggest, I mean. So I'm trying to set it up. So here, the 2, 4, 7, it's in order. We're looking at them one at a time. So we see the 2. What does this mean? We need a 2. 100% we need a 2. It's not possible. So then we see the 4. What do? Well, we try to jump to the 4 from the 2, right? So maybe you need another 2. Or instead we could maybe, I mean, if we added a 1, that's not enough, right? Maybe we can instead do a 3 or 3 plus 1 question mark? Maybe? I don't know. Like those are two possibilities, right? 7. Well, if we chose this, then we need a 3, and that's the most efficient solution. Or if we do the 3, the 2, 3, 1, how many? We have 6, so we need need a 1. Or need a 1, but this is inefficient. I don't know. Basically, what I'm trying to do is I'm trying to come up with algorithms. So we have to look through these scores one at a time from smallest to biggest, and we need to um, kind of use numbers greedily, or like we need to reach the score with what we have, and try to add until we hit the score. We hit a chance to get the score, but we're not we're not set on it, I guess. Um, what was it trying to say? Um, yeah, it's just like we have to like we can't take more than we need. Like we can't just add a bunch of ones, right? We need to do the most efficient step at every single step. And then when we get to later steps, it's possible that we may need to delete a previous action. Like maybe before we needed a 1, but now we don't need a 1 because 2 2s is more efficient. I guess a good example is 5 7. No, 4 6 5 7. Like, okay, so let's say we have a 4 7, right? So how are we going to reach this 4, right? Or maybe 4 6 7 would be good. Yeah. How are we going to reach this 4? Well, we're not even close to the 4, right? So we need to add some sort of, ideally a 3, ideally something really big to get to this 4. So maybe we add a 3, and suddenly our range of possible values. So there's two things here that are important. There's range. So can we reach the question? Can we reach question? And then the second thing is precision, I guess. I'll call it precision. Can we actually hit the point value of the score? Can we hit the point value? Or not the question. Can we reach the score, and can we hit the point value score? So an example when we might have range but not precision is if we have, let's say, 8, just one question, it's 8, and we try to do 3 3s, right? Obviously we can reach the score of 8 by 3 3s, but we don't actually end up hitting 8, so this is not a good configuration. Hopefully that makes sense. So when we see a 4, we try to improve our range by adding a question with a point value 3. So what happens then is we shift our range, and now what we need is a well, we have the 4 and we have the 3, right? We got a 3, so we add a 1, a question with 1, right? And we can hit this 4 now. So now we move on to the 6. So how are we going to hit the 6? Well, we can either +2 or +3 works. I think I'm going to do +3. Actually, this is efficient. Yeah, this is fine. So +3, +1, +3, and this is enough to hit all 3. Now what happens if we instead use 2s? So let's do +2, +2. So instead of using a +3, +1 to hit the 4, we use 2 2s. Then we need something to hit the 6. So this is actually not efficient. Yeah, so we need to hit the 6 and the 7. So yeah, so we need a +2. That would be 4 questions, which it would be a suboptimal solution. So not very good. So here, let me write down what the issues are with an O of n algorithm, or the algorithm that I'm trying to come up with. So we might pick up a question that we don't need in the future. That we don't need in the future. Yeah, if we're just trying to hit I think in the example I gave, this was a good example, right? The threes, where is it? Right here, yeah. So if we try to, we picked up two twos. I mean three. We picked up four fours. Actually, yeah. I like. It's unclear. It's difficult. I think this might be a concern. We might pick up a question that we don't need in the future, or maybe we do need it. Who knows? Or maybe we do need it. Um, Question mark. Um, any other problems? Yeah. So we need like a way to like possibly scrub previous decisions, like remove and replace as we iterate through the array. Okay. So algorithm one, range, how far we can currently go. So then what do we try to do? So let's just say our range is currently like 4. And we get a new value. So here we're able, with our current questions, we can hit 4. So we also keep track of we have an array of used questions. So it starts out with 0, 0, 0. So what does this mean? This means that we've used 0.1 questions, 0.2 questions, and 0.3 questions. So this is the number of 0.1 questions that we're using. This is the number of 0.2, and this number of 0.3 questions we're using. So let's just say with our current range, we're able to hit 4, and now our new question is here, or our new score is sitting at here at point value 9. So we need to somehow get to 9. So here is what I suggest we do. We add 3s until we get close enough to 9. And what does this mean, close enough? I'm not sure. And then after that, we add the difference between 9 and our range. Add difference between 9 and range. And the range is a lot bigger now because we added 3s. A lot bigger now. And then finally, adjust. And what do I mean adjust? So it's a good example for this. 4, 7. Let me make this 8 instead. Yeah, and let's just say we got to this 4. So okay, let's say our current used value is 1, 0, 1. So in order to hit this 4, we have used 1, 1 and 1, 3. 1, 1, 1, 3. Point question. In order to hit that 4. So we are really far away from 8. So we add 3s until we get close enough to 8. So we add 1, 3, and we get to 7. So we from step 1, this becomes 1, 0, 2. So now we're very close to 8. So then we add the difference here. 2, 0, 2. Why? Because we're 1 away from 8, and in order to hit the question 8, we can add a 1, and then we'll be able to hit the point value 8 because we can hit the point value 7. Because we can hit the point value 7, we add a question with point value 1, and we can hit 8. So we got close enough. We added the difference, and now we can hit the point value 8. However, now we need to do the third step, which is adjust. So as I mentioned before, having 2 1s is never efficient. So what do? We replace one of these 1s with a 2. Very easy. And then maybe we could also adjust this, but should we convert this to a 3? I don't know. Possibly. If we don't need a 2 and we could benefit more from having a 3, then maybe we should convert this to a 3 because it might come in handy. Because what if the next question has point value 9? If we don't convert it to a 3, then it would be inefficient. I don't know. The question is, do we need do we need a 2? In this case we don't, right? Yeah, in this case, no, wait, we had the 8. So can we hit 8? I feel like we might need the 2 to hit the 8. Yeah, so these are the sort of questions I saw. Basically what I did is I came up with a bunch of rules like, oh, if we have 2 1s, then we should convert one of the ones to a 2. Then if we have a lot of 2s, then we should probably convert like way more 2s than we need. Then we can replace, for example, 3 2s by 2 3s and save one point. Things like that. One question, I mean. Things like that. So this is algorithm 1. I think this is the one that got me 34 or 35. So let me write down algorithm 2. Algorithm 2. Algorithm 2, I think, got me 29 out of 35. Maybe 32 out of 35. I don't know. So here's algorithm 2. So let's just say, and I think this, for me, this is the algorithm that makes the most sense. So let's just say we can get to, let's just say we have 4 and 6. Or let's say 3, 4, 6, like this. So what are we gonna do? So we start at 0. We have a range of 0. And we're gonna try to hit 3 by adding a 3. So after the first loop iteration, we have 3. We've used a 1, 3. So 0, 0, 1. And we have one question has a 3. So then how do we hit the 4? Well, see, this is I kind of drew this on the number line. So our maximum range is 3. So that's how much we can go. And now we get a 4. So what are the possible ways we can hit a 4 given that we can get to 3? So either we can add a 1 here, add 1, or if with our current points we can hit a 2, can we? If we can hit a 2, then I think we would prefer instead to add a 2. Why? Because 2 offers us more range. So if we get a 5 here, suddenly we don't need to add another point after that. So a 2 is more preferable. But even more preferable than that is if we're able to hit this point, then it would be even more preferable to add a 3. So of course this depends on whether we can actually hit these 1 and 2s. And how do we know if we can hit it 2? Or how do we know if we were able to reach this point with the point values that we currently have? How do we know we can reach this 2? Well, it's easy. If we have a 1. Why? Because in order to get this range, so this range represents the sum of all of our points. So as far as we can go using all our points, represents sum of all our points. So how do we know we can hit this 2? Well, we can use all of our points except 1. Use all points if we have a 1, except 1. And if we do that, then we're able to land here. And then if we add a question of value 2, then we're able to land on the 4. Hopefully that makes sense. Same thing goes for 1. So how do we know we can reach this 1? Well, if we have a 2, that means we can, because our range represents the sum of all our points, that means that we can use all our points except the 2 to get the 1. And then if we add a 3, then we can get to the 4. And it's preferable to use the 3 rather than the, is it preferable? I'm not sure. But this algorithm is a lot simpler. Is it preferable to add a 3? I hope. A 3. I hope. I guess the other thing is it's possible to overshoot. What I mean is if we add a 3, so let's just say our point values are 3, 4, 5. And right here, actually 1, 3, 4, 5, wait, 1, 3, 4, 5. Actually, with a 1, we would already be able to hit this 4. So that would be confusing. So let's just say 1, 3, 4, 6. I think that would work. So you'd be using 3, 1. I don't know. I can't think of an example right now. Is it preferable? I mean, there were definitely times in the when. Okay, I'm just gonna go on because this wasn't working. So algorithm 3 that I came up with was. So here's what I noticed. What I noticed is that there's actually a finite amount of optimal um, like solutions. So let me show you. I mean, an example. So let's just say I have 12, 14. Okay, so these are really big numbers. So we need to somehow get to this 12, right? And then the 14. So how do we get to the 12? How do we get to 12? The answer is questions of value 3 with point value 3. It doesn't make sense to use questions value 2 because it'll take way more questions to get to 12 with point value 2 than point value 3. So this is what I was like, the intuition that I was talking about before is just add a bunch of point value 3 questions until we get close enough to our target. Now, assuming we got close enough to our target, so what does it mean close enough? So before I argued it between a distance between 0 to 3, that's close enough. But actually, I thought upon thinking about it more, I guess the answer is a distance of between close enough. Distance, let's say less than or equal to 6. I think that's close enough. And basically, here's what I imagined all the solutions. I think this is 29 or 35 test cases. So there might be some bugs, which is why some of these algorithms might actually work. So basically, I try to list out all the possible solutions to all possible. Yeah. So I'll just say, so what I'm trying to say here is that there are a limited number of solutions because it doesn't make sense to use a lot of 1s or a lot of 2s. There's a limited number. There's a limited number of 1s and 2s that you needed to use before you just cram it into the 3s. That's what I'm trying to say. It doesn't make sense to use like 3 1s. It makes way more sense to use 1 1 and then a 3. Something like that, or a 1 2 3. That's what makes way more sense than using 3 1s. So there is an upper limit on the number of 1s and 2s that we need to use, which means that there's an upper limit on the number of solutions. So if we just test all the solutions, maybe that's enough. So let me show you a couple solutions. So here we have 1, or I will write here. So there's our 1, then 2, then 3, then possibly 1 2, then 1 3, then 2 3, then 1 2 3, then I guess I forgot the 2 2. I guess I forgot the 2 2. Did I forget? No, I didn't forget the. So see, 1 1 never makes sense because it always makes sense. It makes more sense to use 1 2. 1 2 3, and I think this might be it. 2 2 3. No, 2 2 2 is 1. I think so. 2 2 2 is in the case when you have 4 6. Then it's more efficient to use 2 2 2 than it is to use 1 2 3. Wait, both of those are the same. Okay. Well, I don't know. Forgive me. Difficult problem. So basically, by enumerating all these possible solutions, then we can, so this is, what I mean by this is, these are the numbers that we need, and then plus some number of unidentified number of threes. Plus some number of threes, because we need threes to reach close enough to the 12 and the 14. But then after that, we can use these like smaller point values to get to the exact point values that we need. So I think this algorithm is probably the simplest to understand. So step one, get close enough to point value. And what I mean by that is distance is less than or equal to 6, And then 2, can we hit the point value? So let me give you an example. So if we're looking at a question that has value 10, okay? So, and we add the necessary number of threes. So how many threes do we need on this one? Well, we need 3 threes to get close enough to 10. 3 threes. Here we're gonna add 2 threes. I mean, yeah, what I mean is, well, actually, if we, close enough is distance is less than or equal to 6, and that's a hard cap. So we're gonna add 2 threes here. 2 threes, 2 threes, just everywhere 2 threes. Like until we get close enough. So if we start out with a range of 0, then we add in 3, 3, and we get to 6. And 6 is close enough to 10. So can we hit 6? Can we hit 10 from 2 threes and then 1, 1? No, we cannot. Can we hit 10 from 2 threes and 1, 2? No. Can we hit threes from 2 threes and 1, 3? No. We can hit 9 though. Then this one is also not good enough. This one works. This one works because of 10. This one does not work. This one works, and this one works. So now we can do an extra step here, which is, if we can't, maybe try adding another 3. Or maybe don't. Maybe try adding another 3. Maybe this is not necessary, given that we have the 1 and the 3. Or maybe what I did is I ended up cutting this out, probably. Yeah, I feel like I ended up cutting this out, and then I added this step. If we can't reach it, maybe try adding another 3. So what happens if we add another 3 here? Then suddenly this 1 is good enough, because we can hit 9, and then add this 1, so this suddenly becomes good enough. Yeah. So what is the point of all this? The point of all this is that in the beginning we have lots of possible solutions to this. All of these plus some number of 3s. However, as we go through the array, some of these, assuming we are strictly like the solution is strictly of this form where it's these numbers only plus some number of 3s, some of them are going to be filtered out. Some of them aren't going to be possible. Like, for example, if a 1 is in our array, then this is not a possible solution. 2 plus some number of 3s. Why? Because we need a 1 to hit the 1, right? And same thing goes for this one, and any solution doesn't have a 1, it's no good for us, because we need a 1 to hit the 1, right? And if we have I don't know, whatever. So the algorithm is go through the points. So algorithm is loop through points. Through scores. And here is our inner loop. So get close enough. Then we're gonna loop through possibilities. And then I'm gonna put 2 arrows here to show that it's an inner loop. So can we hit it? Hit it. If not, throw away. Throw away. So this is still O of n because the number of possibilities is limited. Can we hit it? If not, throw away, or try adding a 3. And then at the very end, when we're done through all of this, just return the lowest number of points needed. So it's possible. Obviously, this 1, 2, 3 is always going to hit all of our points, but this might be inefficient. Actually, yeah. So this 3, if we do this thing here, where if we can't hit it, maybe try adding a 3. Then we don't need to consider this possibility because we'll be looking at adding a 3 anyway. And same thing goes for this one. Yeah, and I think same thing goes for this one, so we can throw a lot away. So these are the possible possibilities. Yeah, return lowest number of points required. So hopefully that makes sense. So there are 3 algorithms for, and none of them works. I guess I should try look see again if I can fix it. Okay, anyway, hope that was interesting. It was the last question that I haven't solved, so and I feel bad leaving it at least not considered. So thank you for listening. See you next time.